Have you ever wondered how electrons can pass through walls? Well, to understand this, we'll have to venture into the world of quantum mechanics. This is a realm where the rules of the game are quite different from what we're accustomed to in our everyday macro world. Here, particles like electrons don't always behave like particles, they also behave like waves, a concept known as wave-particle duality. This duality allows electrons to exist in a state of superposition, where they can be in multiple places at the same time. Yes, it sounds weird, but that's the beauty of quantum mechanics. It's like a fascinating game of hide-and-seek where electrons play by their own rules, exhibiting behaviors that seem downright impossible in our macro world. So how does this all tie into electrons passing through walls, you may ask? Well, it all boils down to a fascinating quantum phenomenon known as quantum tunneling. Quantum tunneling, a concept that sounds as if it's straight out of a science fiction novel, is actually a scientific reality. Let's dive into this fascinating world of quantum mechanics and uncover the seemingly impossible. Imagine a ball that you throw against a wall. According to the laws of physics we're familiar with, the ball should bounce back, right? But in the quantum world, things aren't so straightforward. The ball, or in our case an electron, has a small chance of showing up on the other side of the wall. It's as if the electron dug a tunnel through the wall and emerged on the other side. Hence the term quantum tunneling. Now you might be wondering, how does this happen? The answer lies in the probabilistic nature of quantum mechanics. In the quantum realm, particles like electrons do not have definite positions. Instead, they exist in a cloud of probability, a region where they are likely to be found. This cloud can extend through barriers, like our metaphorical wall, and reach the other side. So, when we say an electron tunnels through a barrier, what we really mean is that there's a small probability the electron can be found on the other side of the barrier. This isn't because the electron physically tunnels through or circumvents the barrier. Rather, it's because the rules governing the quantum world allow for the electron's probability cloud to extend through the barrier. It's important to note that this isn't just a theoretical concept. Quantum tunneling has been observed in many experiments, providing solid evidence that the laws of the quantum world are very different from the classical laws we're used to. In other words, the electron has a small but real chance of showing up on the other side of the wall, as if it had tunneled right through. At this point you might be wondering, what's the big deal? Why does this matter? Well, quantum tunneling has some fascinating implications. This seemingly abstract concept is actually integral to many processes in our universe. For instance, it's at the heart of nuclear fusion in the sun. Without quantum tunneling, the sun wouldn't be able to produce heat and light, making life on Earth impossible. Now, let's bring it closer to home. Quantum tunneling is also key to the operation of our electronic devices. Every time you use a transistor, which is a fundamental component of all our digital devices, you're relying on quantum tunneling. This process allows electrons to move in ways that classical physics would deem impossible, enabling the functionality of our computers, smartphones, and more. So next time you use your smartphone or enjoy a sunny day, remember, you have quantum tunneling to thank for that.